Hi, welcome to this session by RouteFabric, and in today's session, we're going to be going over memory management in Java. All right, so before I jump into it, I just want to make sure to specify that this is going to be a pretty in-depth discussion about memory. I think it's very important that we thoroughly understand how memory works in our program, and that'll allow us to make good decisions about what objects we should create, when we should avoid creating new objects, that kind of thing. All right, so the plan for today is we're going to discuss how memory for programs is stored in general, and then we're going to discuss segments of data in Java. We're also going to discuss memory allocation in Java, and we're going to talk about the Java garbage collector and memory leaks, and then we're going to look at a quick coding example so we can see how it works. All right, so memory in programming. So whenever a program is run, some memory must be used to store program information. So this is like all our variables, maybe our data structures, like if we have an array or something like that, we need to store that somewhere when our program is running. So memory is known as temporary storage for our computer. So our memory resets whenever a computer is restarted, and whenever a program is closed or exited, anything like that, the memory is also freed. So the memory that we use for our program is not permanent. It's not like storage on your hard drive where those files are permanent and they'll stay there between reboots. So this information that our program needs to store includes variables, classes, objects, and even the code itself, like our methods and functions, things like that. We need to store that as well so we can jump around the code. So in a strongly typed language like Java, our variables are specified and locked into a type. So we already talked about this. Whenever you declare a variable, you need to make sure you specify what type it is. Java doesn't allow you to just create a generic variable unless you're creating like a generic class or something like that. But whenever we declare a variable, we need to specify its type. So why is that important? Why do we need to specify a type? So the reason we need to specify type is because these types are all defined in different ways, and each type uses up a certain amount of memory. So when we're declaring a variable and we specify its type, what we're really saying is we're telling the JVM, hey, this is what I want this variable to be, so put aside enough memory for that. Like let's say we have something like an integer, which is a number, and we have something like a string. A string can be very long, and an integer is just a number. So we can't, they both have their own type, and we can't interchange them like that, because then we'd have to switch memory around all the time. And so as such, whenever we create a variable, we have to specify its type. So for example, an integer on most 64-bit system uses up 4 bytes of memory, and then like a long integer would take up 8 bytes of memory, that kind of thing. So whenever a variable is declared, memory is put aside for that variable. This varies a little bit in Java. Sometimes memory won't be put aside until a variable is actually initialized, because not all variables are necessarily going to be used. Sometimes we forget to use a variable. All right. All right, so memory continued. So memory is organized in different ways and depends on the programming language. So each language kind of decides how they want to organize the memory, but there are a lot of common structures between them. But regardless of what language the program is in, each program only has so much memory it can use, and this is specified by the computer system itself. So your program that your computer is running is given a certain amount of memory, and your computer says, hey, this is how much memory you can use. You can request more memory if you need it, but if you don't and you run out of memory, then the program will run out of memory. So most operating systems only allow so much memory for a program and limits which memory the program can access. So basically what this means is when you run a program on your computer, your operating system will only allow it a certain amount of memory. And this is just so your program can't take over your computer and basically run it into the ground by using up all your computer's memory. So generally your operating system will take care of this. Also notice I said that it limits which memory the program can access. There's a lot of memory on your computer that is off limits because it's reserved either for other applications or it's reserved for the operating system, and this memory cannot be accessed by your program. So as I just said, programs may sometimes request more memory from the operating system. Generally, this is also out of our control. And an important thing to note is in languages where control over memory is granted, like in C or C++, we can directly access memory. we can unintentionally access off-limit memory, which results in the OS killing our program, and this is known as a segmentation fault. The only reason I bring this up is because this is actually not an issue in Java. And this is because in Java, you do not have control over the memory itself. So in a language like C or C++, we can directly access the memory. And there's some good things this allows us to do, but this also allows us to potentially access memory that is off limits. But in Java, we don't have to worry about this because Java is going to take care of all the memory accessing for us. We can't directly access the memory itself in our code. So there are a couple of different memory structures we should understand when programming. So a stack and a heap, and I'll talk about those right now. All right, so the stack. So a stack is a data structure for memory management employed by many languages, including Java. So a stack is what's known as a LIFO data structure. So what this means is last in, first out. So basically, dumbed down, what this means is that when something new is added to the stack, it is the first to get executed. And I'll talk about this a little bit more. So stacks are generally orderly and self-organized as new elements are executed and then popped from the stack, returning control to whatever was underneath it. So the stack generally doesn't get defragmented or anything like that. It's a very orderly memory structure. So stacks are also going to generally be efficient in memory storage, and like I said, they don't get fragmented. So to visualize a stack, I like to think of like a stack of pancakes. So if you think about it, if you have like a stack of pancakes, whenever you cook a new pancake, you always add it to the top of the stack, right? You would never try to like sneak a pancake in the middle or raise the whole thing and put it at the bottom. No, whenever you cook a pancake, you're always going to put it on top. And then when you also grab a pancake to eat, you're also going to grab the pancake that's on top. You're not going to try to wiggle one out of the middle. So this represents a stack pretty well because this means that the pancake that is going to get grabbed first is always going to be the newest pancake. So the pancake that was most recently cooked is also going to be the first one to get picked. So this really represents a last in, first out structure because that new pancake is the last one to be added to the stack, but it's actually going to be the first one that gets executed. All right, so let's talk about the heap. So the heap is a data structure commonly used for memory organization as well and is employed by many languages, again, including Java. So the heap is quite literally a heap. So it is a memory structure that is disorganized and has no overarching structure. So you can literally think of it as a heap, like a huge bunch of just different memory, different data, all just put into one place. So because there's no organization to it, like there is in a stack is like organized up and down. In the heap, there's no organization. So this means that we cannot find the specific memory because it could be anywhere. So we can't say something like, oh, go this far into the heap or execute the first thing in the heap because there is no first. So as such, in order to use data that we have in the heap, we must have a reference or something that holds the location of the memory we want to use so we can access it. So if we have something stored in the heap, whatever it may be, in order to access it, we need to know where it is so we can hold the location of it. So let's say we have a variable or something or an object in the heap and we want to use it, we need to be able to know, okay, it's exactly at this location. So the heap is vast and can grow, but it also has a maximum size because, of course, your computers are limited by their memory. There is a set amount of memory in your computer, so the heap as well has a maximum size. And unlike the stack, the lifetime of memory in the heap is not defined. So what I mean by this is, if we think about a stack, once the top item is done in the stack, control is passed to the item underneath it, and as such, the top item is deleted. So whenever we have a stack of pancakes and we take a pancake off the top, that top pancake is gone, and the newest pancake is now the one that was previously underneath it. So in a stack, our memory gets deleted when it's done. Whenever we take it out, it gets deleted, freed, however you want to specify what happens to it, but its lifetime is defined. So it's going to exist for a certain amount of time, and then it's going to be done, and it's going to go away, and control is going to pass to whatever was underneath it in the stack. However, in a heap, since there is no order to it, the items in the heap will exist forever. They don't have any defined lifetime. So when we create an object or something in the heap, and we say, okay, create an object somewhere in the heap, and then give me the location of where that object is so I can talk to it, whenever we do that, that object is going to live on forever. It's not going to live on for, 10 minutes, 30 minutes. There's no real timer on it. It's going to stay there until we explicitly say, okay, we're done. You can get rid of this. You can free this or you can delete it. But basically, whatever objects or data we have in the heap are going to stay there in between different functions, different methods, different classes. That memory is still going to be there in that program run. Okay, so you might be thinking this is a lot of confusing information, and really, why does this even matter in Java? Well, understanding how memory works is important to understanding how Java specifically handles memory. So in Java, we have the stack, the heap, and we also have the methods area. And there's a couple other data segments as well in Java, but they're not relevant and they're not used often, so we won't talk about those. But so the stack in Java will store whichever method is currently executing and all its variables. So like I said, a stack is an orderly structure. So if we think about our methods in our program as a stack, we can see that we have an empty stack first, and the first method we're always going to add is main. We've talked about that whenever we create our program, main is the method that our program is going to look for. So we add main all the way to the top of the stack, and there's nothing else in the stack, so that's the only thing. And then whenever we call a new method, so let's say we call a method to change a variable or whatever, that method is going to be added on top of main, quite literally like a stack. So remember, we said whatever is on top of the stack is always what's going to be executed first. So now control is passed to our method that we're executing, and main is no longer in control. So this method is running, it's going to keep going, it's going to keep going until it's done, and then whenever it's done, it's going to go away, and now main is back in control, and control is going to be passed back to main. And then in Java, the heap will store all objects. Yes, all of them. In a lot of other languages, you get to choose whether you want to allocate objects on the heap. In Java, you do not have this choice. All objects are going to be allocated on the heap. There are some very, very rare exceptions where the JVM can choose to allocate your object on the stack. If it can detect that object is not going to be used in a greater scope, it'll do that. But generally, this almost never happens, and in a lot of implementations of the JVM, this is not a thing at all. So always assume that every object you make is going to be allocated on the heap. And then the methods area stores our code. So this is where our class definitions are. This is where our method definitions are. This is where all that exists. And the reason we have a segment for this is so our code can jump around. So we can say, go to this method, okay, go to that method, okay, get this information from this class, that kind of thing. So this isn't too important to know. I just thought I would touch on it. So as I briefly touched on, in Java, direct access to memory is forbidden. So in something like C, we have a data type called pointers, which allow us to directly access memory addresses. You cannot do this at all in Java. There's no way to do this. So what this means is that the JVM will decide where to allocate memory, and then we can access our data via our variables, but we cannot access the memory itself. So what this results in is the typing in Java is much more strict, which means we can't really change types unless we use a proper cast. In something like C, you can kind of get around typing because you can directly access the memory, so you can basically circumvent all the type safety built into the language. In Java, you can't do this because we can't directly access the memory. And there's some other things we need to keep in mind with this, and I'll touch on those in a little bit. So it's very important to realize that the objects we declare and initialize in our program are not actually stored in that method, even though they are a variable. So remember I said methods are going to be, whichever method is executing is going to be in the stack. But then I said that all objects are going to be in the heap. So that's kind of confusing because how can we have methods in the stack if we have objects that are going to be in the heap? And then we can have objects within our methods. So how does that work? Well, the way that works is whatever objects we have in our code and we're using them, those are not the actual objects themselves. Rather, they are a reference to an object because all objects are stored on the heap. So like I said, whenever we have something on the heap, we cannot directly access that because we don't know where it is. So we need a reference telling us, hey, this object is over here, so we can access the data for that object. So in our methods, we're going to have reference types, so that'll be like a reference to an object, and the actual data for that object will exist on the heap, and we can access the data through our reference. So when we say something like string name equals new string, something like this, name is simply a reference to a string object in the heap. Name itself is not a string object. So really this can get quite confusing because in some languages you have a character that they use to define a reference, so you know it's a reference. But this doesn't appear like a reference to us. When we use it in our code, it appears as though we're actually acting on the name object. But it is important to keep in mind that the actual object itself is on the heap, and the variable that we're accessing is just a reference. We also need to realize that the new keyword indicates a heap allocation. That's always going to be true. And so we'll look at a little visual real quick so we can get a better understanding of how this works, because it is a little bit confusing. All right, so if we can visualize the stack, like I said, we want to visualize that as an actual physical stack, different methods being put on top of each other. So I've already talked about how main, so we have our main method here, and that's always going to be the first method put into a stack. And then whenever we call another method from main, it's going to get added on top of it. So this method here is the method that is currently running. And then string name here is a reference, and there's a string object in the heap, and string name is really just saying, okay, this string is going to be over here. So whenever we need to access it, it's over here. So you'll also notice this is why we have an issue with scope in Java. So you may have noticed already, whenever you declare a variable within a method, you can't use that variable outside of the method. You can't use it outside of the curly braces. So why is that? Well, that's because whenever we go to that method and it's added onto the stack, it gets put onto the stack on top of whatever method we were on before, and then all the variables are going to be created. And then whenever that method is done, it's going to get deleted. So those variables that we created when we initially ran the method are then going to be deleted when the method is done. So when we have our method and we have the opening curly braces, it's going to go through all the code, it's going to run it, and then it hits the ending curly brace, and the method is going to be popped off the stack, and our variables are going to be destroyed. So this is why it's important to keep in mind scope when we're dealing with our methods, and be conscious of where we're declaring our variables. And if you're looking at this right now, you might already notice a problem here. So you notice we have string name over here, and we said it's referencing some objects on the heap, but our string name is a reference within a method, and we just said that this will get destroyed when the method is done. So what's going to happen here? Well, we have our method, it's going to run, it's going to keep going, and it's going to hit the end of the method, the curly braces, and this method is going to be deleted. So it's going to stop existing, and control is going to be passed back to main. Well, that means that this reference right here, this little arrow I drew, is also going to get deleted because that's what string name is. It's just a variable that's a reference. So this will get deleted, but our string object on the heap is going to remain because these don't get deleted on their own. These will stay. They have an undefined lifetime. So basically what would happen here is if we were to repeatedly call this method, we would get more and more string objects on the heap. And we'll talk about this right now. So what this is known as is essentially a memory leak. So like I said, memory on the heap has an undefined lifespan. So basically what a memory leak refers to is when items are allocated on the heap and then they're never used again. So generally that happens by the reference getting destroyed, and that memory is not marked as freed or deleted. So what happens is that memory essentially gets completely wasted because we can't access that memory in any way because the reference is gone. We lost the reference, but that memory is still going to be alive and taking up space because its lifespan is still going. So as mentioned, local variables are located on the stack, but objects are always on the heap. So memory leaks are irrelevant in the stack because our variables are going to be destroyed when we stopped using them. When we don't need them anymore, they're going to be destroyed because of the whole scope thing and whenever a new method is called within those parentheses. So our variables are going to be destroyed. So it's automatically destroyed once the method is done being run. So this means that the references, like I just mentioned, the references will also be destroyed if we have any of those in our method. So wait, does this mean that we have to free all the objects we create in Java because they're all existing on the heap, and eventually those reference variables we have to them are going to get lost either when a method is done or whenever main is done and our program is done. That's also going to happen. So these need to be freed or deleted at some point. So you might be looking at the structure and you might be saying, wow, well, this looks like there's going to be an endless amount of memory leaks because we're always going to be creating new objects. They're always going to be on the heap, and we're not going to be able to free them because Java doesn't allow us to free them. Well, actually, Java already has a system in place to take care of this for us, so we don't really need to worry about it. So as I stated, we cannot directly access memory in Java. So what this means is that we cannot free memory, and we can only access our objects through references. So we can talk to our objects through a reference, but we can't actually free the memory itself once we're done with it. So what this means is that we'll have references and we will eventually lose those references, but the objects will still exist, and we have no way of deleting them. Well, this is when a tool that Java has called the garbage collector comes in. So in essence, what this means is that we don't really have to worry about memory allocation in Java, since it's kind of out of our hands. Since we don't have direct control over the memory, and the garbage collector is going to take care of any potential memory leaks for us, it is kind of out of our hands. That being said, we really should still have a robust understanding of memory so we can properly optimize our code and write safe code. We don't want to be declaring objects when we don't need to. We don't want to be declaring variables when there's already a variable we can use. And we also don't want to keep objects alive for much longer than we need them. So even though memory allocation is kind of out of our hands in Java, I think it's still very important to understand the stack and the heap and really have an understanding for how memory allocation works in Java. So the Java garbage collector. So remember, all objects are on the heap and can only be referenced in Java. So these reference types are stored on the stack so they can be destroyed. So when a reference to an object is destroyed, the object still exists but is completely inaccessible. So like I said, this would normally be a memory leak scenario. So that's where the garbage collector comes in, swoops in, and deals with it for us. So the garbage collector will free inaccessible heap objects for us. So the garbage collector will look, it'll see we have an object and we have a reference to it, and then eventually that reference is going to go away, and the garbage collector is going to say, oh, well, this object is now useless, and it's basically just taking up memory for no reason, so I'll go ahead and clear it for you. So it's very, very important to keep in mind with the garbage collector that it is completely out of our control. So we cannot say, hey, free this memory on the heap. Hey, delete this memory on the heap. We can't do that in Java. The garbage collector is going to decide when to do this, and the garbage collector is going to run out of our control. So basically, it's going to run whenever it pleases. There's a lot of different algorithms for garbage collection, and depending on your version of JVM, what version of Java you're using as well, that will change. But basically, just know that how garbage collection works and when it's going to be running is going to be out of our control. So all we need to worry about is keeping track of how many objects we instantiate and possibly setting references to null, i.e. they don't reference anything anymore if we don't need an object anymore. So basically what I mean by saying this is if we have an object and we don't need it to be referencing anything yet, or we're done with whatever that object is in the heap and we don't need to access it anymore, we should ideally set it to null. That way the garbage collector will know, hey, this reference is gone, so I can delete this object in the heap eventually. So obviously this is not always the case because our references will automatically be destroyed when a method is done. But if we have a particularly long method or we have something in main and it's going to exist for a long time, we can use null to basically speed up, if you will, the garbage collection process and kind of nudge the garbage collector in the right direction so it can delete an object if we don't need it. So real quickly, we're just going to look at some code. So for simplicity's sake, I've already written the code, and I want to specify that it's not important to understand everything about the code. There's some stuff that we haven't gotten to yet. We will only be focusing on the memory allocation parts of the code, so just keep that in mind. All right, so let me just open up the Eclipse workspace real quick. And basically what I've created here is I've just created a container, a data structure, a linked list data structure to hold any type we want to hold. So as you can see here, I created a list of an integer type. So we're saying this is a list and it's going to store integers, and I set it to a new list. So this right here, if we deploy our knowledge we just learned about memory allocation in Java, what is this doing really? So we're creating an object of the list class. We're instantiating an object, and where's this object going to be put? This is going to be stored on the heap. Why? Because every object is going to be on the heap in Java. And of course, we're using the new keyword here, and we know you should always equate new to heap allocation. Those should always link together in your head. Whenever you see new in Java, you should think, okay, something is dynamically being allocated. So if we look real quickly at our list class, you'll see we actually have a lot of different allocations being done here, and we also have a lot of different objects to keep in mind here. So if we think about our list, we have the actual list object itself, as in whenever we create a list, that is one object. And then the list is made up of other objects because each list is going to have nodes, and these nodes are going to be their own objects. And then those nodes are going to hold data of some type, in this case, integer classes. It's going to hold integers, so that is another object. So this is actually a semi-complex kind of scenario because we're actually instantiating many different objects here. So if we look at our list class here, we have another object which I defined and I called it a node, and then the node has another object which is data. So you'll notice whenever we create a node, we're going to set the data to be whatever we want it to be. So whatever the user puts in, whether it be 1, in this case we're using integers, whether it be 1, whether it be 10, whether it be 5,000, that's what we're going to set the data to be. And then we will also see that we have within our node, which is an object, we also have a reference to another object, which is another node. And we're always going to set this to null when we're not using it. So whenever we create a node, the next node is going to be set to null. So what does this mean? What are we doing here? So we are creating a list object, which is going to be stored on the heap. And then in that object, we're going to have a node object. And in that node object, we're going to have a reference to another node object. And then in each of those node objects, we're also going to have a reference to some data, which is also going to be stored on the heap because these are all objects. All right, so as you can see here, we have the list has a node for its head, as in the first item in the list, and that's also going to be set to null whenever we create a list, so we know the list is empty. When it's first made, the list is going to be empty. Basically, we're saying, hey, there's no nodes here. We're not referencing any node. No node has been created on the heap yet, so we're just going to set that to null. All right, and then if we want to add something to our list, if you think about it, if we want to add something, our list needs to grow dynamically. So we just talked about dynamic allocation. Whenever we do dynamic allocation, what word comes to mind? New. The new keyword always comes to mind whenever we're thinking of dynamic heap allocations. So what we're doing is here we're saying, okay, if there is nothing in the node, so if there's nothing in the list, so the head is not referencing anything. Remember we said the head was the first node in our list. So if it's not referencing a first node, then that means that there is absolutely nothing in our list. So then we're going to set the first node to a new node, and we're going to initialize it with this data right here. So what we're essentially doing here is we're doing a couple of memory allocations. We're declaring a new node and then referencing it with head, and then in our new node, we are setting the data to be this object's data right there. And then we also have a method for adding data to the back as well, and this does the exact same thing. And you'll notice here that if there is something in the list, then it's going to go through the list until it gets to the end, and then it's going to make a new node there. So that's our dynamic memory allocation there. And also note, we can always tell when our list is over, when it's cut off, whenever it ends, by using null, because we know null doesn't reference anything. So if our next node is referencing nothing, then conceptually that means that there is no next node. So our list is at its end. So that's how we're able to go all the way to the end. And then of course we also have a change function here. So what we're doing here is we are basically just going to an index the user specifies, and we're accessing that specific node, which you'll notice here we actually have different references for the same data. So there's actually only one object in the heap if we think about it here, but we are using multiple references. So we have our reference here called head, and we also have another reference called temp, which is just a temporary reference that'll get destroyed at the end of this method. So basically what we're doing here is we're going to keep going through, and then you'll notice temp.data equals data. So this temp is going to actually get destroyed at the end of this. So how is this going to stay? How is our changes going to stay? Well, remember, temp is just a reference to some node objects on the heap. So we can have multiple references to the exact same object. We can do that. So what we're really saying here is we're not changing the reference stays the same. We're saying change the actual object, and the object is going to stay alive, of course, because it's on the heap, and we still have our list. Our list still exists, presumably. Our list still exists since we're calling a method to our list exists, and in that case, we will be able to access that same exact object. All right, so if we just go to our where our main method is, you'll notice we created a list using new here. So we created a new list object, and then once this is done, some other objects are going to be created. Not yet though, since it's empty, like we said, the head, which is the node reference to the first node object, is going to be set to null. So we know that the list is completely empty. So we know the list is empty. And remember we said whenever we call a method, this is going to be put on top of the stack because methods are executed in the Java stack. So whenever we call l.addFront, that's going to go right on top of main in this case, and that is going to be the method that is executing right then. So whatever is going on in AddFront, which we just went over, we briefly covered what goes on in AddFront. We're going to be allocating a new node object basically. That is going to occur first, and then control is going to be returned back to main. So we're going to do this method. It's going to go, and then it's going to get, control is going to be pushed back to main, and then we're going to be able to do this method, same thing happens, and then this method. And you'll notice with our methods, the temporary variables that we have in our methods that are not part of the class, basically, whatever those may be, those always get destroyed. So whenever you see temp here, you might be saying, well, won't we get like a conflicting declaration error? Because we declared temp here, but we also declared temp here. You can't declare the same variable twice. Well, since these are going to be executing in their own methods, and like I said, methods stack on top of each other, and the variables within those methods get destroyed when the method is done executing, these are in a different scope. So we're allowed to do these because this temp right here, whenever we call int size, this temp is going to be declared, and then whenever size ends, it's going to get completely destroyed. So whenever we call another method, temp actually doesn't exist. Java has no idea what temp is, so we're allowed to make another temp variable, which is going to be a reference. So I hope this lesson was informative. If you would like to learn more about memory management in Java, be sure to check out our lessons at RouteFabric.com. Thank you.